Our presenters today are Jeff Fuser and Craig Trumpy. Jeff has over 30 years of experience in process control and particularly pump reliability and fluid sealing. Jeff spent the last 20 years with Able Technology and Field Services, which is now a Novaspect company, and is currently the Business Development Manager for Able, where he's responsible for helping customers with their fluid sealing solutions. Craig Trumpy has over 20 years in the process control industry with experience in control system engineering, as well as selling Delta V control systems. Craig is currently the Director of the Machinery Health Group for Novaspect, where he's responsible for delivering CSI Emerson condition monitoring solutions to the marketplace. He is currently a board member and past chairman of our Upper Midwest chapter of the Vibration Institute. Craig and Jeff's teams work together across all industries to improve customer operating costs using world-class technology and local service. So welcome, guys. Thank you for being here and sharing your insights with us. I'm going to turn it over to Jeff now.
Thank you, RB. And thanks. Good morning to everyone that's out there listening to this. We're going to be talking about, my section will be Pump and System Analysis 101. And we're going to talk primarily, getting to the first part here, it's going to be on the basics of a pump and system analysis. As you can see, that there are many different pump designs out there. You have pumps over here that are centrifugal, split case, many different designs, submersibles. To begin this course with, we're going to actually start with the ANSI pump, the basic parts. We got the thrust bearing, the radial bearing, the volute, or the casing as it's known as, the impeller, the discharge side of the pump. We got the suction side of the pump. And typically have a mechanical seal or packing area in the pump. Inside here, these bearings will typically either be greased or oiled. The majority of them are oiled. This is a typical API 610 pump. It's built a little bit heavier duty. You can see that a little bit more support out here. And there's a few things that are different than an ANSI design pump. Of course, safety factors and a much more heavy duty type of pump. On the next slide here, this is a double suction pump. The reason why I'm showing this here is just to get an idea. You see this plate that actually channels the fluid to two sides of the impeller to up here. So it gives an even load on the impeller and there's less hydraulic load on the shaft and the impeller. So I have a vertical turbine type pump. I'm only showing a couple of these designs just to give you a better idea of all the different pump designs that are out there. This pump is considered a little bit higher pressure. Okay, the next sheet coming up here, this is going to be when we talk about analyzing a pump. This is typically where you're going out, you've experienced a pump failure and you want to know more about it. This is the type of information that's going to be required on that that you're going to need to know. First, you got the manufacturer's pump curve. With that, I'm going to be showing you a pump curve here in one of the next slides. This is very critical. You're going to need to know that when you're looking at a particular pump. Then you have the pump impeller diameter that's going to show on the curve. Or you're going to need to know that. It should be stamped on the casing on the side of the bearing frame, typically. Because you're going to need to know where does it correspond to the pump curve that you have. The hours of operation is important. Is it a start-stop operation? Is it a batch system? Do you have it for on for 4 hours, off for 4 hours. Your pump suction and discharge pressures, definitely measured. It's preferred with a gauge or some type of device that could tell you what that flow is. And then you're going to use that to determine the actual total dynamic head, which is TDH. Your actual flow rate, measured preferred also. Then you're going to want to look at the system configuration. Is there more than one pump in service? Are they running up against each other? How does the pump interrelate to the other pumps? Are they series or parallel? I'll have a slide on that, series or parallel, and what the difference is. In your sealing system, do you have packing or mechanical seal in there? What type of environmental control scheme? Then going up to the motor data, you need to know the full load, the size, horsepower, voltage. You will need to know all this information. It's very critical in analyzing what's going on in your system. Fluid properties. You're going to need fluid type, specific gravity, percent of solids, type of solids. This all has a lot to do with the life of your pump when you put this all together, so it's going to be very important. Your past failure history. Has it failed 3 times in the last year? Has it failed 6 times? Has it ran for 10 years? It's very important information. So we're going to go into the pumping system to understand that, a little detail on this. Here's your typical pumping system. You have your suction side coming in, feeding the pump. You have a motor that's putting energy into the fluid, turning the pump, transferring the energy into fluid. Whoop. I hit the button, so I jumped the slide. Sorry about that. Here's another typical pumping system. You have the suction line going in, coming out of a tank here, feeding this pump. This pump is then pumping it up into a sprayer system. So you just get an idea of the suction coming in, going out. And in this suction line, you will have a valve typically to shut off. Okay, pumping system. Here's what's required for a pumping system. Your hardware, you have a pump, a sealing system, the motor we talked about, the base, foundation. You have your pipes and tanks. Your process fluid environment, percent of solids, temperature, flow, stability, regulatory compliance. You're looking at your utilities and instrumentation, your practices and procedures. You'll have operating practices, you have your maintenance practices, and you also have your purchasing policies. These two here, the operating practices and maintenance practice, are very critical in how people are operating these pumps. And an example would be one of the procedures or policies you should have is when you start a pump, what are the proper ways to start a pump? What are the proper ways to shut down a pump? There are differences in how you should do it. And then most important of all, you have the people, the operators, the maintenance techs, engineering, plant management, purchasing, suppliers, and vendors. So as you can see, the pumping system is just more than hardware you see. There's many different factors that can be causing poor reliability, and you need to understand this and identify these factors before you can find a sound solution. So we're going to talk about the pump curve now, which I started off with the kind of information you need to actually analyze a system. And so the curve is going to tell you a lot of information. A pump curve is of a typical pump will perform. It's going to have your pump information on it, your total dynamic head, feet or meters. Typically, it states here it'll be in feet. Then your total dynamic head, and this little equation here, it's quite simple. I'm going to repeat this at the end of my portion. Your discharge head minus your suction head, or you could go discharge pressure minus your suction pressure and calculate that back into total dynamic head by the same equation. In suction lift applications, it's very key to understand that the suction head will be a negative number, and therefore it's added to the discharge head to calculate your total dynamic head. This total dynamic head here is 50 feet minus a negative 10 feet is going to give you 60 foot of head. Your capacity, the pump curve will be on there, efficiency, brake horsepower, and net positive suction head required. And there we go. Takes a little while to load some of these curves up on here. Okay, we're going to start off right on this left side of the curve. If you see this up to 750, 0 to 750, that's your total head, total dynamic head, TDH. Right alongside that, you're going to see these inch marks. Those are a 13-inch impeller, a 12-inch impeller, 11, 10, 9. This is what the one pump will actually be able to support, a 9-inch to a 13-inch impeller. Over here on the upper right-hand corner, you're going to see the size, 1.5 by 3 by 13. That is the maximum size impeller. This 1.5 is your discharge side of the pump, and your suction line coming in, which will feed the pump, will be a 3-inch. On the upper, total upper, it's going to be your net positive suction head required. And that'll be in feet also. And then right below that, these are your best efficiency points. And you're looking at 60% is your best efficiency on this pump curve. You also will, further down, you're going to have your flow. It's going to be 0. This one goes all the way out to the end of the curve line, which is approximately 650 foot of head. But as you cut that impeller, your flow will also, if you're putting in a 9-inch impeller, for example, it'll only max out at 450 foot of head. I'm pulling up another curve here. It's going to show a little bit slightly different type of impeller. You'll see the different size here. You have a size of a 10 by 10 by 26, very large pump. Your net positive suction head required is actually down here on a little bit different scale. So not all curves are identical. It depends on your manufacturer, but the majority of that information should be there. You can also see that your total head of feet is only goes up to 55, not 750. And your flow, but your flow increases way out here. It's just a totally different size pump, but with a 10-inch suction and a 10-inch discharge coming in, it can handle that flow. Now we're going to talk a little bit about the system curve. How much flow can the system handle? So the system curve really is you're plotting out of the friction loss as a function of flow. So you're going to have losses, and these are friction losses. So you have static lift or head coming in. You have your pressure heads. And the other thing that can really cause a lot of friction would be your piping and your fitting. So that would be your valves. Control valves is a good one that you put in front of a pump. It will really cause a lot of friction inside the system. To just gravitate back to a little bit of a curve look at it, you got your head, and the more friction loss, the head increases as the flow increases, so your velocity. So your friction loss just skyrockets as the head goes up and as your flow goes up. So we're going to talk a little bit about the pump operating point. The intersection of the system curve with the pump curve is where the centrifugal pump will operate in a given system. Moving on to this next slide here, and I'm going to be going through these quite quick because I have a lot of slides that I'm going through to get some of these points made. So I'm going to move through them quick, and if there are any questions, I'm sure you can be more than happy to. I'll be more than happy to answer them for you. On this particular curve here, we're looking at the best efficiency point where you're running, and where that right there is your pump operating point. And that's what, it's not so much your design point. You might have designed it totally different. You might have designed it here, it's a 500 foot of head at 550 gallons a minute. Your design point maybe is up on this curved line or this impeller line, or it might be down here, off to the left. You try to get as close to the best efficiency point when you're designing a pump for that system, when you're designing a system for that pump. Now, what ends up happening when you're, let's say you are operating here, that's great because everything feels real good, very little vibration coming off your system. But if there's an example would be if you have a control valve down on the downstream on the discharge side of that pump and it starts to close off, you're closing that off and slowing the flow down, you're raising the head, and as you come out of here, you're getting away from that best efficiency point, or that BEP. And at that point, this is when vibration is going to start, as you get away from that. If you happen to design your pump out here, let's say over here, you are already causing that pump to, you're putting vibration and radial loads onto the impeller at this point back here. And the further back you go, if that control valve keeps shutting off because that system is saying I don't need that flow, and you can start operating over in here, you're looking at catastrophic failures and you're shortening the amount of time that pump will operate for you. As you bring it back here and that control valve opens up, vibration goes away, and now you could have an issue. And the same thing will occur as you come back off and away from BEP and start getting out in this no man's land, I'll call it, out here. When that happens, you'll also experience a lot of vibration coming from over here as that control valve, let's say, opens fully. Yeah, and this curve is showing you a little bit more detail of something that I was just talking about. Here's your best efficiency, and here's where we try to run that pump. But as you start pulling away from that best efficiency point, you're going to start seeing discharge recirculation. You have the control valve closing, and now you're starting to recirculate coming off the cut water inside the pump. And you have the suction recirculation occurring. The further you're getting away from BEP, the more damage you are doing to your pump. And then on the right side, you go into a high flow cavitation. And all the way over here, you can actually go into a low flow cavitation. High temperature rise. When you're deadheading a pump like this, you're imparting a lot of energy, which is heat, into that fluid, and you're raising the temperature of your fluid that you're actually pumping. Here's a little bit more simplified look at it, and now we're talking the radial force on the impeller. So as you're running a BEP, you have very little radial flow. That's what this, you're at the bottom of it. It's running smooth. You walk up to it, you lay a cup on top of the bearing frame, and you don't see any vibration coming off. You start pulling away, and as you get percentage-wise off of your gallons per minute on the left or to the right, BEP, your vibration is going to start increasing. It's going to be moving back in this direction, the radial load on that impeller. So what you are doing is you are actually bending the shaft with the radial force being applied to the impeller. That's not a good scenario for that pump. They don't last very long. Bearings won't hold up that long if you have this kind of radial loads being applied onto the impeller. Now this poor little pump shaft is got a lot of work ahead of it when it starts going into these points beyond BEP. As you can see, you've got up here on the upper right, an impeller radial thrust being applied. At the same time, that impeller has an axial thrust. You have hydraulic-induced forces acting in another direction, and you actually have a hydraulic imbalance coming off the ends of these, or the tips of these impellers. This poor packing or seal that's up here it's trying to stay as flat as possible. We lap our seal faces. The manufacturer that we sell for laps our seal faces to about 3/millionths of an inch face flatness. It's trying to maintain that without opening. You have a radial thrust being applied due to the impeller and the misalignment that could possibly be in there, and that's that radial impeller load. So this bearing has taken all this energy when it's trying to deflect and try to stay there. And then you also have a radial thrust due to impeller misalignment on the thrust portion of it. And then you have an axial load. If you have misaligned, you actually have axial load. So these two little bearings are the workhorses in trying to keep your pump running and your process and your systems moving. So as this happens, I'm going back to this BEP again, and this is the key thing. If you pick up anything today, it's that best efficiency point. How close is my design point to my best efficiency point? As you can see, the loads with a little bit different impellers, but your vibrations do pick up as you pull away from BEP. And Craig's portion of it, he's going to talk a lot about this when you start pulling away from your BEP and how we're going to go about monitoring those vibrations. So the pump operating range. Therefore, to improve your pump reliability, it's important to first know where the pump is operating and then take steps to bring it back into a safe, reliable operating range. So the information that I gave you prior to this all starts playing a role in why you want to take a look at this to analyze the system. So I'm going to just go over a few terms and concepts here, understanding the pumping system. Tom mentioned about pumps running in series or running parallel. This particular one is a setup with a pump running in series. And if you look down here, we've got 50 gallons a minute at 40 foot of total dynamic head, pumping right into another pump. And this is not uncommon in facilities process to do this, to increase the amount of head. As you can see, the flow did not increase, but the head doubled. And you have, let's say, two same size impellers, so one is pumping, picks that up, and then just doubles your head. And in parallel pumping systems, the head is constant, so 100 foot of head stays the same, but the GPM doubled. So when you try to turn on another pump that's pumping into a header, for example, you're not going to gain any more total dynamic head, but you are going to double the flow going through these pumps. There are scenarios where one pump, and these are tough applications because one pump could deadhead this other pump if it had a different size impeller. It's key. If you're looking for that, if this is an 11-inch impeller on this pump, and a 10-inch impeller on this pump, its flow will go to 0. You will not increase your flow to 100. It'll stay at 50, but it will put out more head. If this is the same, then they'll both compete with each other. I want to talk, I'm going to spend a couple slides here on net positive suction head. And the A is available. That's what it stands for. What do you have available to feed that pump? It's the amount of pressure expressed in feet or meters which is supplied to the pump suction. This is so key when we start talking about cavitation to check this in your systems. The amount of pressure available is a function of the suction system design. You have two possible conditions. One is, am I lifting the fluid up to the pump, or is it a flooded suction? Do I have a tank above it feeding this pump with a lot of head flowing into it? This is your suctionless design. The good thing about this is you got atmospheric pressure helping you out. If this tank is enclosed, you don't have that additional pressure to be put on this fluid and to bring it up to this suction side of this pump. This is a flooded suction side. Now you have atmospheric pressure pushing down, plus you have from this height down to the suction side of this pump as available. This is available, not required. We'll get into the required in a little bit. So the calculations, and you know, one reason why I just put the screen up, I don't want to go into a great deal. I'm not going to bore you to death with functions or calculations here. But the note is this right here. Is right here. I got to go back. Is a centrifugal pump does not suck the liquid into itself. That's the key thing you need to know. The pressure on the surface of the liquid actually pushes the liquid into the pump suction. It's very key to understand. Now we talk about the NPSH, the net positive suction head, the parameters of it. Absolute pressure is acting on the surface of the liquid. So an open reservoir has, you get an additional 33.9 feet. And that's calculated out from 14.7 psi. So if you were to take 14.7 psi, times it by 2.31, you're going to get a calculation of 957. In a closed reservoir, you don't have this to help you. So you're going to either have a positive or a negative, which would be in a vacuum. And a good example I'd use would be a condenser unit that operates in a vacuum, but yet there's a level of liquid above that pump. Those all have to be calculated out. So when you're sizing that pump, you'll get it right on what kind of NPSH available you have. And you have absolute pressure, the atmospheric pressure plus your gauge pressure. You have 14.7 plus 50 psi, or another way, you can look at it, you have, let's say, 39.9 feet. That comes from atmospheric pressure, plus 10 foot would give you 43.9. And if you're operating in a vacuum, you have to calculate the opposite. This note here, units must be the same. That's at PSI must be PSI. If you do your calculations in feet, you must do it in feet. We have net positive suction head required. This is what the pump curve is asking, telling you you need to have. In order for that pump to not cavitate, you need this, it's required. So this is the amount of pressure expressed in feet on that curve that we looked at, required by a centrifugal pump as to not to cavitate. The specific NPSHR for a pump can be found on the manufacturer's pump curve like we just mentioned. Okay, so this is the net positive suction head required that we had just talked about. 6, 10, 16, 20, right down the line. What I want to bring about here is that's what's required, but if you look, as the flow increases, so does the NPSHR. So we start off with 6 feet at a very low flow on the pump of 200 gallons per minute. But at the best efficiency point, this 60 here, in the center, it's asking for about 20 feet. So if it was an open tank, flooded suction, you'd still have enough atmospheric pressure, so we'd be at 33 feet. We could actually, if it's an open tank, flooded suction, at 30 feet, you could also get that also there. Key thing here to understand, to avoid cavitation, the NPSH available has to be greater, and I would recommend 2 feet greater than the NPSH required. Yes. We had a question that just came up, does NPSHR depend on fluid type and temperature? It absolutely does. Hot water, let's say you're running hot water at 150 degrees F, you're going to have the different specific gravity, and then that brings into play your vapor pressure at the eye of the impeller. I would love to go into a lot more detail as these questions come up, but I'm going to be limited on time. So we are going to be just a note, a little advertisement here at this time. These questions come up, it makes me think of it. We are doing conferences this year. One of them will be held in Milwaukee at Miller Park, and it'll be on this type of information for pumps. And we're going to have Craig Jumpy there, and we might even have a speaker with wireless technology on it also. And then we're looking at doing one more for in the Wausau area this year. So I'm going to go back to this cavitation. Cavitation is a condition when the liquid that's entering the pump suction begins to vaporize. As a result of a pressure drop experienced in the suction eye of the pump's impeller. We've got a little chart coming up here in a little bit, and it's going to show you what we're talking about right there. On this chart here, we have the A here, so you have an entrance loss. Now these are pressure drops. It's what actually is coming into the inside of the impeller. So as this comes in, it's going to meet this impeller, and you have friction right here at this point, which is B and C. You start seeing a more pressure drop, and you have a turbulence right in front of the impeller, and that's where you get your lowest pressure drop. And if that temperature and type of fluid hits your vapor pressure point, it's going to vaporize, and that is what you're talking about as far as cavitation. On the onset of a recirculation, which it was mentioned there before, cavitation can occur in a pump running at BEP. You could have that happen if your NPSH has not been met, the required. Whereas recirculation occurs when the pump is running away from the BEP flow towards the back. As you go back, you're going to see more recirculation, and that's because downstream, as the valve gets closed, because the system's saying, I don't want as much flow, I can handle the more pressure, but I can't handle that flow. As that control valve starts closing, we start running into these situations where vibration starts getting picked up. If you ever heard the cavitation noise, you can also possibly hear recirculation occurring. Or if you see wear on the side of the volute, you'll know if it's recirculation or cavitation once you pull the pump apart. Okay, the location of this impingement damage to the impeller for both cavitation and recirculation, you're going to see it on the impeller itself when you pull it apart, or you've heard the noise, or the pump, the efficiency starting to get, you're not getting the flow you want, you'll start noticing wear patterns on your impeller. And they'll show up here as damage from the recirculation or the cavitation. You'll look on your volute, you'll also see maybe where the tongue meets that inside the volute, you'll actually see that wore back, wore off, and that's the sign that you have recirculation going in there. And really, when you take a whole look at this, is the pump designed to run near the best efficiency point when you have actually sized your pump? This next photo here that's coming up, you can actually see what it looks like. This is actual cavitation damage here. Each one of these blades is wore back from the actual damage caused from cavitation. And now your impeller is not balanced. You start getting much more vibration coming off of it and picking that up. Okay, things to consider in analyzing a specific pumping application. And this is getting towards the end of my presentation, but these are some of the things that I take a look at when I walk through and down into a facility and they say, hey, we got a pump that keeps failing, would you take a look at it? Questions I'm asking myself, where are you operating on the curve? Are you left or right of the BEP? how far is the pump's operating point from the pump's BEP? Are you how far to the left or how far to the right? And the only way I'd really know that is if I took a look at the discharge pressure and suction pressure and do a quick calculation. Take the suction pressure minus the discharge pressure times 2.31 divided by specific gravity, and that's sort of in reference to the question that was asked, equals your total dynamic head. And then the other question I typically ask is, has anything changed in the system that you have maybe just changed in the last 3-4 months prior to this failure taking place? I've seen it many times where an additional line was added. A work order got cut. They added a line downstream, wash down, for example, and they picked up the flow on the pump. And so now that pump is operating more to the right of BEP, or the design point. You have a line plug or following up restriction. Or if it's pumping out of a tank, did the tank level drop? Are you meeting your NPSH available, your suction side? These are just some quick questions you can answer and almost analyze that system real quickly. Process temperature increase. You're concerned about that vapor pressure. Suction or discharge valve's not properly working. And then the other thing is, when they install these pumps, is there any pipe strain? You want to know that right away. And if you have to be down there when they're taking this pump apart, watch to see if those suction lines or discharge lines are jumping away. So by answering just a few questions, it will lead to increased mean time between failure. So the conclusion, an analysis of a pumping system is fairly simple if you understand the basic concepts, and I hope I've given you enough, not to get yourself in trouble, but enough to go down to your systems and take a look at them. Or when you get that bad actor, take a look at it, contact one of our specialists out in the field or myself if you're not sure, and we can come out and take a good look at it. And that concludes this portion of the webinar. I'm going to turn it over at this time now to Craig Trumpy, and he'll go into pump health monitoring.
Okay, thank you, Jeff, and well done on the overview of pump systems. Thanks again to everybody for joining us today. Hello, this is Craig Trumpy with the Novaspect Reliability Group. Next up, we will move into monitoring for pump and machinery health and how pump and equipment monitoring can help extend the life of your pumps and other plant assets. Here are a couple of challenges that we're trying to address with pump health monitoring to essentially manage and predict pump failures. You can see that, do you have unexpected pump or machinery failures? Do you have monthly or quarterly route vibration programs and still have misses or unexpected failures? Do you have vibration monitoring on essential assets, but you find that the alarm is too late to plan maintenance or avoid the failure? And additionally, does your vibration analyst see a problem, but operations continues to run the machine to meet production, resulting in complete failure or production upset and or increased repair costs? If these are the cases, then you're in the right place to discuss this today. Here we are looking at a scenario that may be too close to home for some of us, but clearly our goal today is to make you aware of the technologies available to cost-effectively upscale your current health monitoring beyond what you might be seeing today. The Emerson CSI product line that we are focusing on today is specifically around mid-tier pump health monitoring. We do have portable analyzers and full online systems. We are specifically looking at pump health monitoring in a cost-effective wireless application. It would be the way and technology of choice today. If you look at the pump health monitoring available, it goes well beyond vibration. You can see here you can apply monitoring that is appropriate to you, whether it's vibration or whether it's on your seal water levels, your seal system levels, discharge or suction pressures are all available, and you pick and choose what you need for your particular application. When we look at pump health monitoring, some of the failure modes that we are looking at and the different measurement technologies that we would apply for each of these failure modes are listed here. So as you have the background on the pump system from Jeff, this will help you understand and select which measurement technologies would apply. A P&F curve here is really just looking at what we're driving with this new technology is to move you up and to the left, earliest indication of a problem, so that you have time to plan maintenance and avoid an unplanned or unexpected shutdown of your production. So here is an example, again, with the Emerson Pump Health Monitoring concept. We are suggesting that you pick and choose what issues you're having, what you need to monitor today, what fault conditions, and you apply the appropriate measurement technology at that point. One example of a way to start or an entry point for pump health monitoring might be a single vibration monitoring device. This 2-channel vibration monitoring that could be as simple as 1 accelerometer per shaft. Or if you have a scenario where you get continued or chronic plugging of your strainer, you would look at applying a differential pressure measurement across your strainer and bring that into your operating system as a early warning of a problem. So again, you pick what you need, where you need it in this pump health monitoring solution. So when we get into, we're going to just drill in a little bit here into early bearing fault detection using some new technologies from CSI Emerson, and really help you differentiate between overall vibration, which is the way people have looked at vibration for a number of years, and understand the new measurement or additional measurement that we call PeakVue. The difference of the failure modes that we identify, which each vibration is listed here. Overall vibration, the traditional vibration, does a very good job of identifying failure modes of imbalance, misalignment, loose foundation, bent shaft, and late stage bearing failures. In comparison, the PeakVue measurement that's looking at the higher frequency of the vibration waveform, and specifically looking at the peak Gs, is very good at detecting lack of lubrication or early bearing failures, cavitation, and friction and looseness within the bearing itself. So really 2 distinct measurements, although we're pulling it off the same sensor or accelerometer. Drilling a little bit farther into understanding PeakVue and overall vibration, specifically for the bearing failure case. You can see the chart here, and the overall vibration is really lifts off very little until there's a significant failure, a very late stage failure in the bearing. In PeakVue, you see the column here, you start to see a lift off of the PeakVue measurement in the early stages of a bearing failure, and allowing you the time to plan for your maintenance on this problem that's coming at you. Here is another way to look at and understand overall vibe versus PeakVue. Again, this would be just time on the bottom here and trying to set alert or fault alarm limits for these failures. You see in an overall, it's just not enough movement to create an alarm that doesn't create a nuisance problem for you. With the PeakVue, we are moving really to the left here, trying to pick off an early warning of a failure so that you can plan for it. And we get enough movement with the PeakVue measurement that we can set the alarm limits and really not create any nuisance type of alarming. So let's just look at a case example here. This is an actual failure that occurred in mid-January at one of the plants we were working with. The blue line on the bottom is the overall vibration measurement, and the red line is the PeakVue measurement. The significance here is really that with a monthly program, this failure went from showing very little problem to a big problem in less than a 30-day route. So if you have guys that are doing 30-day routes and they miss a failure, this is not that they're not seeing it in the vibration spectrum. It simply is a failure that's occurring in a shorter timeline than that. And here is a look at the actual defect of that of a bearing in that case. And here's a close-up as well. So maybe we could see a raise of hands of anybody that runs this type of a square element in their plants. I don't know if you have a look at you there, there's ability to raise your hand, but feel free to do that and we'll get a count. So again, what we're trying to do here is upscale your current vibration monitoring, predictive monitoring from what hopefully you're not seeing in your plant today. Moving on, I've got just a 4-slide vibration 101. It's what I'll claim is the world's fastest Vibe 101 course, and we'll just give you a little more background into the technology behind vibration. So here you see a pump with many frequencies of vibration and varying amplitudes occurring, whether it's in a pump or a motor. And what folks are doing, and you hear vibration analysts talk about spectral data, we are simply splitting out those different frequencies of vibration so that we can look at the individual amplitudes. And overall vibration that we've been talking to up until this point is commonly used in plants today. It is looking at this lower end of the frequencies, and where higher amplitude problems show up, specifically misalignment or imbalance or significant foundation looseness. What we are adding to that is this PeakVue vibration measurement, which is looking at the higher frequency, lower amplitude vibration issues and driving toward an early warning of problems that could be occurring in your pump or machines. So again, another example here is a dynamic of what we'd consider an overall vibration. If you walked up to a machine and you could see it vibrating, you could feel it, that's an example of low frequency or overall vibration. It works very well for shutdown applications. And coming up here is an example of PeakVue vibration. It's taking a little bit to load the dynamic here. Or it's taking a long time to load the dynamic here. So here you see the vibration occurring, and what we're seeing there is a defect on the inner or outer race, creating a small impact. And the significance here is the characteristic of this vibration. It's an impact, or it's a sharp spike. And what occurs, and we'll show you this on the next slide. What occurs in a defect on a bearing is a sharp spike. It's similar to your car, your tire hitting a pothole in the road. And what we're doing is we're monitoring a very high rate to capture the peak, the true peak of this waveform. That's what PeakVue is doing. There are other folks that are using high frequency to get early warnings, they are often using a root mean square or an average of this waveform. And as you can see here, there's on these impacts or these spikes, there's very little area under that curve, so it does not lift your average or your RMS signal enough to create an alarm that's real meaningful. PeakVue is capturing this peak, allowing a lot of movement and allowing a much easier time setting warning alarms and critical alarms. So we'll go into some case histories. I just got a few case histories to help show a couple of the example failure modes that we have identified. And the first one, this is a boiler feedwater pump at a paper mill. And you can see again the blue line is the overall vibration. The red line is the PeakVue vibration. They were having unexplained seal failures on this boiler feedwater pump. And we put on the monitoring here and we're able to identify that they had intermittent cavitation going on that they ultimately linked back to the way they were operating this pump. The next example is on a high-speed pump with a gearbox in there to increase the speed. We were monitoring PeakVue and overall as well on this. The overall is on the green line at the bottom here. Monitoring a gearbox with the gears meshing together, we have a normal case where we have a baseline of PeakVue at 19 Gs. In this case, this customer is running alarm limits and operating procedure that requires operations to move to their backup pump in the event that they go into alarm condition, which is what occurred here. And so the operator turned the pump off, moved to the spare pump. The next day, the vibration analyst was able to come in and do a full analysis on the pump and identify that it was a bearing problem on the intermediate shaft of this gearbox. Third example, or case history, is for early warning of a lubrication issue. There's actually two cases in this one. The initial scenario is this purple line that went high. This was a dryer fan, and the scenario that happened here, the root cause, is that the vent on the oil glass was blocked, and upon unscrewing or opening that vent, the oil came out of the oil glass into the bearing, and the PeakVue measurement went down. They continued to add oil until the PeakVue was lined up, and the beauty of these examples is that if we can catch them at the lubrication issue, we can avoid the failure altogether. The second case at this site was this green line, and you can see this was running about 14 Gs. After our experience with this first fan, we looked closer at this fan. And what we found is a sight glass that was running low, and they decided they needed to run more oil in here, and they're in a much better position. You saw the PeakVue come down when they added oil to the sight glass. The scenario that threw them off on this fan is that they had their sight glasses a little bit off of level, and so we indicated we had a high PeakVue and they wanted to add oil to this bearing. We actually told them the PeakVue was indicating this one is light of oil. Even though they were showing more oil in here, you could see that looking at the level here, they were actually low, even though they could see oil in this sight glass. So coming back again to this scenario, again, this is an early warning of a bearing failure that simply would not be caught with a 30-day route. It would be very, very difficult to catch with that. And bringing us back to our P to F curve that we had looked at initially, the idea is to get as far early warning as you can by extending that P to F interval. That would create a less frequent measurement case. So you want to measure your data here at least 2 or a half, in this case 10 days. Every 10 days you'd want to measure to be able to pick off this problem. And so I think where an application for monitoring beyond a route-based might apply. A bonus case history we have, it's not a pump application, but we get a lot of interest and questions around it, is in a wind turbine application, so I thought we'd just share that briefly. In this case, we deployed, and you can deploy this pump health monitoring in a mobile or portable basis. So this was brought to the top of the tower. The connections for the accelerometers are magnetic and installed in 10 to 15 minutes in the nacelle of this wind turbine. And we were able to monitor the different bearings in this and access this through the internet and a cellular modem. And we monitored, in this case, 2 turbines. The first turbine, the bearing health on the PeakVue measurements were good. And you can see to the right here, we put on a second turbine where there was a known bearing issue, and you can see that the PeakVue indicates a bearing issue for them remotely. So that covers our case histories, and I guess I challenge you at this point to ask, is your monthly route the right frequency for monitoring this mid-tier of assets or your essential assets within your plant? Let me just, there we go. So that concludes the slide portion of this. I would like to just recognize and thank our principals, Chesterton and Emerson, for providing a lot of the material and slide information that Jeff and I were able to use for the presentation today. So with the question answer, thank you everybody who's joined us, and at this time we'll take any questions live, or you may also contact Jeff and or I directly with any questions you may have at our contact information shown on the screen.